Hello, let's find out how differential protection relay is working. It is highly utilized in transmission and as well as distribution system. So let's find out how it works, the basics work. So differential protection works by comparing the current in against the current out. So meaning that the current differential protection compares the sum of all the current information obtained between the two ends of the protected zone of protection. So it compares between bus A and bus B, meaning that what is the current in, compares the current in against the current out on here. So it is working based on Kirchhoff's current flow. So the zone of protection covers the area between two seats to the protected component, for instance, a feeder line. So this is the protected area. Okay, this is what we need to protect. So it compares what is the between the area between the two cities, because the cities are used to measure the current information. So the concept of unit protection satisfies two problems that would not be achieved using overcurrent protection. Of course, overcurrent protection is used for a backup protection in transmission system and a main protection in distribution. So the choice is why we choose unit protection is because a unit protection has a successful grading for a complex network. It can also provide the same operating time for all faults within the protected zone. So for example, regardless of the fault location, it provides the same time, the same operating time. But in overcurrent protection, well, it is different because it can slow down. The operating time will increase as the fault is away from the relay location because of the impedance or the circuit of the line. So and then again, if we compare against the distance protection, well, unit protection on short lines provides a better coverage for resistive fault. The problem with the distance protection is because distance protection struggles to see faults near the relay, especially in front of the relay or just behind the relay, because distance protection works based on impedance measure. So it is less accurate for close-up faults, but unit protection is more it's better compared to the distance protection. Well, how does the mode of operation or selectivity works on unit protection or differential protection? Well, differential protection is a form of unit protection that compares the measured current signal at both ends of the feeder. So it compares at both ends of the feeder. So when a trip signal is sent by a differential element, so for example, we have a one relay on here, relay 2 on here. This is the actual relay, physical relay type example. So then it trips to the local circuit breaker. We have the circuit breaker on here, or circuit breaker 2. So for example, if this relay sends a fault, then what it does is it communicates to the channel and send a differential inter-trip signal to the remote relay. So this relay will say, okay, trip this one, send the information to that one, and trip the circuit breaker to here. And isolate the system, the fault system, or clear the fault basically. And then this will ensure that both or all the end of this protected zone will be checked. Again, we need to understand, well, how the relay behave during internal and external fault. So if we look at during the internal fault, so we have a fault on here internally within the protected zone. We're supposed to protect this element. But if what happened when a fault happened on here, well, let's say that this is the current coming through. So normally when there is a fault, and then this is another source of the current or fault current, when a fault happens, all the faults are trying to come to the fault point. So the fault point is coming as a source of fault. So fault is coming to that side, and then from that as well on here. Say, for example, we have another source from here and another source, regardless. So just like this for assumption. So now, if we look at on this one, the seed measures and then the CT current flow is opposite to the primary relay, so the line current. So it goes that way. If you look on this one, then the I1 on here convert. Okay, so meaning that the unit protection senses the differential between input and output current. So it senses between this and what is in and what is out. So let's have a look. So now, before this current come that way, and then this come that way, okay, and then another current is coming that way, and then I1 become as equals to I2 on here, but they are not equal because if you look on this one, there is something like a current is coming that way and then it's coming that way, so they are not equally. It's not like acting. It's not going like this. It's not going. So if they are to be equal, it has to go like this way. But now this is coming that way. So and measure from here, and then this is coming that way. It's the opposite way. So this current is not zero. Okay. So if we look at this tail, the operating principle of differential protection during internal fault, where the fault is located on 50% of the line. So the I1 P, I2 P, meaning that the primary current at bus A and bus B, whereas I1 and I2 are the secondary relay currents. So that in this case, the differential current is net zero, meaning that they are not zero, that the summation of this current is not zero. That means there is I differential. So this current differences will flow in the relay, so that flow in the relay, and then the relay will close it to the local circuit breaker. That's how it works. So that's how we detect, because if the total summation are not equal to zero, the relay will sense. How about during the external fault? Well, during the external fault, okay, say this is the current source or the current flow from here to the fault point, all of them, so that we compare this current against this current out, okay? So under non-fault condition or during external fault, non-condition is non-fault condition is non-fault or internal. So there is no any fault in the protected zone. So their difference is supposed to be nil or small. However, this assumes the CT does not saturate. Okay. So if we look at on here, how does this mean? So for example, this current is going that way and it's going that way. Okay, and then this current is going that way and then it's going that way. So it's in and then out, so that there's two. I1 is going that way and then I2 is going that way, meaning that their summation is like zero, because this plus minus is zero. Okay, so for that reason, so basically, as you can see, so this current going that way, whatever is in is out on here, so that they're zero. So the zero means there is no differential current, and then the zero current in the relay, hence the relay will not cause relay to operate, so that this relay will not be tripping, because the fault is not within this zone. The fault is outside of the protected zone. So, well, how do we set? How is configured? How do the relay set in? So the principle of differential protection compares, of course, as we said already, the difference between current entering and leaving the node. So the protection operates when this difference exceeds threshold value. So how do we calculate this settings? For instance, if we look at, we have the three sources from here, or n number of sources. So the current setting will be, say, for example, I differential on here, IA plus IB plus IC. And then bias current is this one. Bias current will be IA plus IB plus IC divided by 2. And then K1 is the first slope. That is differential current divided by bias current. And relay operating criteria is, for example, for bias current less than I is 2 here. I differential has to be greater than K1 times I bias plus IS1. So, well, how do we know this? And then for above this one, for that line, okay, this one is for this one. And then the second will be for the above this one. That means this is the equation. So then what are the values on here? How do you find it? Well, we just listed on here, and then it's typically, it is just from the Alston protection information. So it can, the minimum setting current, for example, is just 0.2 times nominal current on here. That means 20% of setting, the minimum. And then on here is 200% or 2 times nominal current. Certainly, this is just a 30%. And of course, this is the 150%. The reason for this one is because we need to ensure that the relay is stable and the heavy support current. So, well, if we look at how we can calculate the relay setting, so assume we have a CT measurement error between CD1 and CT2, which is an amount of 5% and 10% in phase. Okay, normally we just ignore about this one. But so now if we consider the differential protection must determine the minimum percentage by setting K1 and minimum release of setting current IS1. Now assume relay P1 or on here, that's relay 1 and relay 2, measures the external fault. So if we have the external fault on here, okay, so that we have a CT2000 divided by 1, or the relay secondary current is 1 amp. So we just divide it by 2000 so that we have 7.3 amp, okay, the secondary current to the relay. So the relay P2 measures the external fault current, and I2 5% higher, which is slightly to the higher because of the error, that it will measure that 7.665 at an angle of 10, because there is just, this is an assumption. Okay, so I1 will be 7.3, but I2 will be 7.6 because of the error of the measurement CT. So the differential current will be this, I1 minus I2, that is, sorry, 1.35 amp. Okay, now we have to calculate the bias current. What will be the bias current? The bias current or the restraint current as I1 minus I2 divided by 2, that is a 7.4 amp. So the minimum bias setting K1, which is this one, is 30%, or I differential divided by I restraint. From a default, it is 30%, but because we have to calculate from here, that if we calculate, it's around 80%. Okay. Now, since the feeder normal load current is 2000 on here, what we need to do now is the CT secondary current is 1 amp, and the CT error has this magnitude. That I2 will be 105 times 1, that is this one. So the minimum setting current, or IS1, that is IS1, that is the K1, that's K2. Okay, so we found out the K1, which is this one, 80%. And then IS1 will be I1 minus I2, that is 0.185. Normally, by default setting, it was 20%, but in this case, it is 18.5%. so that this is 18.5%. So the relay will sense when there is any differential current around 80.5%. So that's the bias setting characteristics of the relay operating treatment criteria will be I differential will be 80% times the bias setting of bias current, which is this one, plus the 18.5% of the setting current. Okay, so the differential current is that one, so that the relay will trip in this area basically. So in this area, sorry, to divide this one. So in this region, with this kind of equation. So what about the application of differential relay protection? Well, the differential protection or unit protection is a very effective way of protection scheme. So we can use, because of it provides high sensitivity, fast operation, and 100% selectivity, which responds well for faults within the protected zone. And we can use in many applications. However, a differential protection cannot provide a backup protection on an adjacent line because it only protects within the protected zone, whereas distance relay can cover 50%. What does this mean is, if, for example, we have many bus bars, okay, the differential protection protects only, okay, within this one. So it doesn't provide any backup for the next line. But the distance protection, what we're saying is, distance protection, it can cover like zone 1 on here, 80%, and 125% zone 2, and then zone 3 maybe 120, 125 or 50%. Okay, so the distance protection provides a backup to the local or to the adjacent lines. Okay, but the unit protection only protects us for the protected zone only. So that, however, since differential protection uses only cities and provide 100% protection coverage, it is also used for generator, transformer, bus bar, or bus and motors. However, distance protection we normally use for a transmission system or sub-transmission. So the unit protection is often chosen or it is highly applicable for, especially for weak sources, because it is based on the current differential. So for instance, if we look at one of the applications for transformer protection, so if, for instance, we have a transformer delta star urgent, 400 kV down to 130 kV, so we could calculate the full load current to be 346, for example, on this one, I1. And the secondary current will be, we have to divide by the city. That is 0.56 or 0.577, sorry. So on the LV side, the full load current will be 1050, and then if we divide by the CT ratio, it is 0.88. Okay, now each city should be corrected to the relay rated current. In this case, because our relay secondary current is 1 amp, so we have to divide by 1. So the HV ratio correction factor will be 1 divided this value, which is 1.77, and LV ratio or correction factor will be 1 divided by this value, so that 1.1 portion. This setting will be entered to the relay. Okay, so this is just the basics, but we have to also consider the Gardner resistor and neutral resistor calculation. But this will hopefully give you just the basics to the differential